Okay, let's start. So this is lecture 12. So last time we talked about, for the last couple of times we've talked about causality in quite a lot of formal detail. We've talked about chronological future and past and so on. Then we've talked about talked about causal diamond, then domain of dependence, Cauchy hypersurfaces and global hyperbolicity. And with that, we have sort of set some stage to discuss general relativity. There's a little bit remaining, and actually I thought it will take me 2 lectures, but depending on how things go, we might even be able to do the rest of it today, either that or today and the next time, and that will complete our formal results on causality. So actually time-wise, things are going surprisingly quite fast, and if you want to slow them down, you only have to ask some questions and I'll be happy to go slower. So one of the things we proved last time was that in a globally hyperbolic space-time, first of all, what is it? Is one with a Cauchy hypersurface. We usually call it Cauchy surface, but I'll also use that terminology. But it's a hypersurface, that means codimension 1. So this is from last time. And what is a Cauchy surface? So it's one whose hypersurface whose domain of, well, let's not, we don't need all the words, d of sigma such that its domain of dependence is the dependence. Now the result we proved last time was that topologically M is equal to, I'll put it this way, sigma cross R. That is if it's globally hyperbolic, of course. Otherwise, obviously, we can't say anything. It's topologically the direct product of a Cauchy hypersurface with the real line. This tells you a few things. First of all, a globally hyperbolic manifold must be non-compact because the real line is not compact. The second thing it actually tells you is that the Cauchy hypersurface itself is compact as a subset of M because sigma is the same thing as sigma cross a single point, and a single point, so any point you pick from R, just call it, let's say, the origin. So sigma is sigma cross this point, and this point is, so let me just see the statement before I think I said it, I didn't mean compact even, I think I meant closed, sorry, I wrote the wrong thing, closed as a subset of M. So O is a closed, or single point is always closed in a manifold, O is closed in R, and therefore sigma cross O is closed in sigma cross R. So the Cauchy surface is always closed. Okay, by the way, there's a more formal proof that Cauchy hypersurface must be closed in M, but I think the simple argument is that sigma is just sigma cross 0. There's a more formal proof which will be in my notes. Okay, so let's do one thing now. Let's talk about maximally extended spacetime. You might have used this terminology. You might have seen this terminology used in studies of gravity. So the idea is this. Suppose I have a globally hyperbolic spacetime. One thing we know is that we can certainly shrink it or consider a subspace of it, and that will still be globally hyperbolic. Because the statement is that all curves, inextendable causal curves, should pass through a given Cauchy hypersurface. So to take a trivial example, take Minkowski. So let's say this is sigma. Now I can just arbitrarily cut off my Minkowski spacetime here and here, and even remove these dotted lines, and so I have the spacetime which is just in between this time and that time, and then it just ends. It's still globally hyperbolic. Okay. Conversely, so we can restrict to, let's say, from minus t to plus t, and this is still globally hyperbolic. So you can ask yourself the converse question. Suppose somebody gave me only this piece and said, here's a globally hyperbolic spacetime. What can I make it larger? And in this case, of course you can make it larger. You can simply expand it to fill whole of Minkowski, and it will remain globally hyperbolic. So you can think that anytime I can take a space-time and enlarge it, that is embedded in a, as a sub-region of a bigger space-time, I can think of the bigger one as an extension of the smaller one, and then at some point I might not be able to extend anymore, keeping it globally hyperbolic. Okay, so the concept is very intuitive. Maximally extended space-time. So, maximally extended means cannot extend anymore. Now, it may not be very easy to argue this, or there may be an indirect method. Obviously, you can't sample all possible extensions and conclude that none of them is there. You have to find a method to prove that you cannot extend anymore while preserving globally hyperbolic property. Then we'll call it maximally extended. So this is a useful concept to keep in mind, because sometimes what happens is you have coordinates which artificially restrict your space-time. So you might actually be working with this part of Minkowski. Okay, this is not a good example because this part of Minkowski itself can be mapped onto the whole thing. But you might have a region and you might have a coordinate which with some tan function or something goes from minus to plus infinity, and you think, okay, my manifold is over at these places, but actually it's not. And you already, I'm sure, know the classic example, which is of Schwarzschild, where you can extend it by going to better coordinates. So it's just good to have this general rule. Okay. Now I'll turn to essentially the last topic in the discussion of causality, and that is the space of causal paths. I used to think this was a very difficult thing, but now I realize that it's no more difficult than anything we've done. It just transfers many of the statements that we have become used to into a slightly different language, which is, instead of the space of points, the space of paths. Now, the space of paths has awful, potentially awful things about it because it's infinite dimensional. This is in a way also one of the problems people realized early in string theory, which is that while the theory of point particles just fill a finite dimensional manifold, but all possible string configurations make an infinite dimensional space, sometimes called loop space for closed strings, and that's a much harder space to work with. Okay, so the space that we are interested in now is the following. We start with a point P, we end at a point Q, and we consider a curve which goes between this, and we imagine it's parameterized, so we could call this curve as x mu of lambda. We don't restrict it other than saying it's causal. So it could be partly time-like or partly null. It can't be space-like. Okay. Now, of course, in order for a causal curve to end at Q, starting from P, it must be that Q lies in J plus of P, by definition of causal future. Good. Now we can choose lambda so that, just for convenience, so that this point, the beginning point is x mu of 0, and this point is x mu of 1. So lambda just goes from, so the parameter goes from 0 to 1, and we trace the path. This is just a convention, but the point of making it is that we might be talking about a given path. You might have one convention, I might have another, but we should agree that if our paths can be transformed to each other just by reparameterizing lambda, then it's the same path. Okay, so now we give a name to the set of all causal paths. From P to Q. Of course, if we fail to choose a Q in J plus of P, then it will be empty. That's also a valid set, but it's not very interesting. So we'll assume always that Q is in the causal future of P. Okay. So this set will be called, denoted CPQ. So in this picture, we can imagine that these paths look sort of like this, or like this, or like this, okay? But they cannot look like this, because this one has space-like regions, so this will not be causal. So there will also be non-causal paths from P to Q, but that's not in the set CPQ. Okay. Okay. Now, as I've said, this is an infinite, the space of all such paths, even causal, is infinite dimensional. I hope that's obvious and I don't have to prove it. The point is that I can vary any region of this path by a tiny amount to get a new path. And since I can break it up into as many tiny regions as I like, each path has like infinitely many variations. While for a point, there are only finitely many directions it can move. Okay, but still, we are going to define a topology and then prove a theorem. So define a topology on CPQ. And the topology will be defined in the following way. Supposing, we assume we have a topology on the manifold M already. Okay, so let U be an open set of M. And for practical purposes, we'll consider the U which is large enough to include both P and Q. You can also choose them to include only P or only Q, but you just get a trivial outcome. So let's take U to include containing both P and Q. Now, given that open set, we can ask what are all the causal paths which are fully contained in that. Okay? And so define O of U to be the space or the set of all paths in CPQ that lie fully inside U. So in this diagram, of course, the space-like path anyway I don't even want to consider. And let me say this is my U. There could be in principle a causal path, suppose depending on how I choose U, like that. There could possibly be a causal path that strays outside U and comes back in, then it's not inside O of U. It's still in CPQ, but I won't say it's inside O of U. So O of U is a set of paths. Okay? Now U was an open set of the manifold, and I'm going to say that, declare that O of U is an open set of CPQ. This is a declaration because I'm defining a topology on CPQ. I can define it how I want. And topology is always defined by saying what are the open sets. There could be other ways, but that's the standard way. And so I'm saying that for every U which is an open set of M, O of U is an open set of CPQ. Okay. Now, it's not enough to just say this. I have to prove that this definition satisfies the axioms of topology, which say that arbitrary unions and finite intersections are also open sets. Okay, so but it's quite easy to see that if I take a union of these open sets, then I'll get something which is such that, okay, if I take a union of two O of U's, I'll get something which is again O of some other U. You have to work that out as an exercise. Arbitrary unions and finite intersections. So if I take the union of any two O of U's is an O of something, intersection of any finite number of O of U's should be an O of something. So you have to construct that thing, but with that it defines a topology. On CPQ. Now, why are we interested in the topology on CPQ? Because topology is a space of is the study of continuity, and we want to think about varying curves continuously. It's not surprising because after all in GR we have so many interesting curves like geodesics, and we have so many interesting bad possibilities like a missing point or missing region in a manifold. And one way to detect a missing point or region might be that if I try to deform a curve to another curve, maybe there's a point or a line missing which stops me doing that. Okay, so this topology will probe that, and as you know, those missing objects can destroy global hyperbolicity. So it won't be a surprise that in this topology, CPQ is compact, turns out, if and only if the space is globally hyperbolic. That's the equation. Did I write that already, the theorem that CPQ is compact? Or did I just define? So theorem. CPQ is compact in this topology. And I mentioned briefly yesterday that the mathematician Leray very long time ago, let's see, is the earliest reference in a way, hyperbolic differential equations 1952. That's even before I was born. So these are some lecture notes on this problem of hyperbolic differential equations, and he actually proposed that a manifold should be called globally hyperbolic if CPQ is compact. Okay, but we are going to say that this is true. So that was his definition of globally hyperbolic. We already have a definition which is the existence of a Cauchy surface. So then for us this result is a theorem. So actually historically what Garrosh did in 1969 in a very beautiful paper called Domains of Dependence, strongly recommend reading it. It's only 13 pages. Let me write it here. It's really one of my, it's such a lovable paper because it's as free of excess formalism as can be. This is the title of the paper, 1969. It's very nicely explained and it has many examples. And many things were defined here, including for the first time domains of dependence. And what he did was to say, okay, CPQ being compact, let's assume, and let's show that the manifold has a Cauchy hypersurface, and also that if the manifold has a Cauchy hypersurface, then CPQ is compact. And he didn't exactly say in those words, but at the conclusion of his paper would be, therefore we can reach this definition in favor of what I call Garrosh's definition, namely that globally hyperbolic means there is a Cauchy hypersurface. Then this is an implication. So that's why it's a theorem for us. For him this was the definition and the other thing was the theorem. Okay. And Garrosh had in his paper, in that paper is a very nice quote. He says, the compactness of CPQ requires intuitively that there be no asymptotic regions, in quotes, holes or singularities in the region between the points P and Q. That's the intuitive. So unusually among practitioners of this subject, he gives these intuitions in his work. So sometimes Hawking's papers are frustrating for the fact that there's some theorem proved in 3 lines, but there's not much intuition given for why it should be so. Okay. Now, you may think that, okay, this is all good, but really in any system that we know, the space of curves will be compact and will be, because finally compactness is related to convergence of sequences, and convergence of an infinite sequence of curves seems quite intuitive. Like if I had those curves which I drew between 2 given points, and if they sort of get closer and closer, then you would think that they should converge in a good space to a limit. But this is not how curves work at all, and this is why there's a right away a problem. So I can immediately show you a family of curves which don't converge to anything. So, but they are not causal. So this is why CPQ in its definition as causal is the space of causal curves between P and Q. That's absolutely crucial. So if we drop causal, then curves can have very bad convergence. So here's a famous example. Let's consider P to be here and Q to be just here. This is T, this is X. This example is given in Witten's lecture notes on light rays. Maybe it's also there in earlier literature. So let me consider a curve which goes like this. So this is sine of pi, x equals, it's just the sine curve x equals sine pi t. Right? So for t equals 0, x is 0, and then for t equals a half, this is t equals 1, 0 to 1, and for x equals, for t equals 1, again x is 0. So this is this curve. Now let me put an n here, integer. So a generic curve in this family does this and ends there. Okay, so now let me assume that this is the nth curve in my sequence. Does this sequence have a limit? That is, does it have a limiting curve? What happens as n goes to infinity? It's hopeless. This thing just zigzags wildly and it never converges. There's no limit curve or convergence curve. Then I haven't defined convergence curve, but right now I'm using it in an intuitive sense and I'll be defining it precisely. But this also can't possibly be causal. All these curves in this family are non-causal because all of them have space-like parts, and in fact get more and more of that as they zigzag more and more wildly. And that's because they can, obviously. But now if we consider a curve which is causal and from a point to another point in the future, then the wild zigzag is restricted by the fact that they are causal. So the statement is only true that this space is compact when they are causal, and we'll see that then this convergence behavior, this bad convergence behavior doesn't exist. Okay. Now, since we are trying to say that prove that a space is compact, I think I'd like to review compactness again. So actually, in a way, maybe I gave that example prematurely. You may wonder why I needed convergence for compactness. Actually, there are several kinds of compactness, one of which is called sequential compactness, which exactly involves convergence. So let me just survey that. So the compactness simply says that every open cover, so that's a cover by open sets whose union includes this set, this space, admits a finite subcover. So there's a famous example of why if you take an interval, an open interval is not compact. The interval which is one dimension, open interval which doesn't have its endpoints. This is non-compact, and the way to show that it's non-compact is that I can just take this midpoint, call it 0, and define a sequence of open intervals which keep increasing. Okay, I hope you can see from this what I'm doing. You can write them, you can even do it actually. You can just say minus 1 minus 1 by n up to, sorry, what am I trying to do? I want them to increase. Yeah, I think this is correct. So from minus 1 plus 1 by n to 1 minus 1 by n. Think of open intervals which start at minus 1 plus 1 by n and end at 1 minus 1 by n. So if n is, for example, 2, let's say n starts from 2, then it's minus half to half. If n is 3, then it's minus 2/3 to plus 2/3. So it's what I have drawn here. It's an expanding family of open intervals. Now, if I take the union over all n, then it clearly covers this given open interval from minus 1 to plus 1. Because pick any point in this open interval, it's clearly it's clearly in some of these. Okay, wherever you pick a point, there will be some n large enough such that the point is in one of these open sets, so that makes it a cover. But is there a finite subcover? No, because there is no finite subset of this particular cover which actually covers the whole space. So you see that? A finite subset would mean that I name the values of n I'm keeping. I'll give you a subset of open intervals for n1, n2, n3, n4 up to say n100 or million, it doesn't matter. And this is my cover, I claim. But whatever is your largest n in that finite set, I'll be able to find a point still closer to the boundary here, which isn't in any of your finite cover. So in this case, so we conclude that open interval is not compact. So very simple example. Now a closed interval, however, is not compact, yes. A closed interval is not like that. In the closed interval, we enclose the endpoints, so it is -1 to 1, including all the points, including -1 and 1. And now simply this cover fails, because this cover, it's an infinite cover of the open interval, but it doesn't include the point 1. If I name the point 1, it's not neither in any of these nor even in the union of all of them. They'll come arbitrarily close to 1, but they'll never reach 1. So this anyway doesn't work. If you now work a little harder, it's hard to prove that something is compact. It's actually easier to show that it's compact, because then you just have to find, what is easier to prove? Every open cover admits a finite subcover. I think the problem is that, So it's, I was right. To show that it's compact, I just need to find one open cover that doesn't admit a finite subcover, and I did that for the open interval. But to show that it's not compact, I have to prove that, to show that it is compact, as in the closed interval, then I have to, in principle, consider every open cover. Now, who's going to consider every possible open cover? You never work like that. You can't simply list all open covers of some given topological space, so you need to resort to theorems. Now, in the case of the intervals, there's a simpler result, which is that this is called the Heine-Borel theorem in calculus. It says that for real numbers, compact is the same as closed and bounded. So, but please be very careful, only for real, for Euclidean space, let's say. It's not a general theorem. First of all, Euclidean space is a metric space. Might be able to generalize it to other metric spaces, but it's basically given in calculus, multivariable calculus, where my multivariables span a Euclidean space. Then compactness is equivalent to closed and bounded. Closed means containing all the limit points, and bounded means bounded. It's since there's a metric and there are numbers here, bounded means all the points, let's say in 1D, all the points are such that the mod of their x value is less than some x0. Okay. Now you can see that the open interval is not closed because it doesn't contain its endpoints. So every sequence doesn't converge to an endpoint in it. So it's not closed. Of course, these names are distracting. They're chosen precisely to fit this idea. The closed interval is closed. Okay. The full real line is closed, but it's not bounded. Okay. Good. So this is the distinction between compact and non-compact, and we could have imagined using this, but this also really doesn't work for us because it is metric spaces that we want to embed in some Rn, then it will work. Now the problem here is that actually we don't even have any Rn because the space of this CPQ, these curves, is infinite dimensional. So we really are in a very tough spot trying to prove compactness. Okay, so of a space of curves is really hard. because of its infinite dimensionality. Happily, there is a way out, and the way out is to change to find an equivalent definition of compactness, which is easier to verify. Okay, so there's a concept called sequential compactness. And let me state it and then tell you what is the relation to compactness. So sequential compactness says that I'll define it more formally, but every sequence of curves, so every sequence, not curves, this is a general statement, every sequence has a subsequence that converges to a limit in the space. We'll be drawing lots of examples, but basically I'll give you the simplest example with points. So imagine somebody has given you a sequence of points. Okay, so these are like xn, maybe they're all on a line, and this n equals 1, 2, 3, and so on. Now, the space will be sequentially compact. This is in some space, and it will be called sequentially compact if every such sequence not necessarily converges to a limit, but there's a subsequence. So I pick out this n. Let's say, for example, the subsequence could be the even xn's. That's an easy, or every third one, or some other way to define a subsequence. So there should be a subsequence that converges to a limit which is in the space. Then it will be called sequentially compact. For curves, how would that work? For curves, I would like the curves to converge to a limit curve, but actually I don't exactly need that. I just need that given a sequence of curves, given an arbitrary sequence of curves, I should be able to show that I can always find a subsequence that converges to a particular curve. That will be sequential compactness. Okay. Now, it turns out that sequential compactness, so this I won't prove for you, but sequential compactness for what is called a second countable space is the same as compactness. And what is second countable? Second countable is a slightly weakened condition on a topology which says that there exists a basis of open sets of the topology which can be put in one-to-one correspondence with the integers. Okay, it's a second countability is a little tricky. I'll put some notes about it. I'll put some comments about it in my notes. You can, for example, ask that is the usual topology on Euclidean space, is it second countable? So how do we define that topology? By all the open balls. Okay. Now, open balls is not a second countable set because they can have any radius. So the value of the radius is a real number, and the real numbers are not countable by definition. That's a continuous infinity, while the integers are a discrete infinity. But the trick is that rational numbers are somewhere in between. They are dense in the space of real numbers, but they are also countable. We can set up a map between all rational numbers and the integers, one-to-one map. And you might know how that map works. So you could take the balls in Euclidean space to have only rational radius and rational origin, then it's a second countable basis. And all you want is that there is such a basis. We don't need to worry about that. All the spaces we consider and the topologies we consider are very much second countable. So that's the least of our worries. We only need to prove sequential compactness, and we would have proved compactness. But there's a little work involved in proving this property. And we'll do it now. It will take 10 minutes. So please feel free to ask questions. I'm sorry that this is really formal, but it's literally the last really formal thing before we can get to actual physics. And it's needed because all these things and these equivalences get used in the study of geodesics. And of course, you know that Penrose remarkably won a Nobel Prize in physics despite being a mathematician who, in some sense, from early days knew all these basic mathematical concepts and applied them to the study of black holes. There is a practical way to do it, which is to assume everything I've said. But it seems to me that you're never going to get intuition for what he did if you don't go through some of it. And this is, my discussions are much less rigorous than let's say what Walt puts in his book. I mean, they're not necessarily less rigorous, but they are less formal, at least. So this is the best you can do if you really want to get to the important results that people have proved. Good. So now let's now actually address sequences of curves, and we'll keep studying sequences of curves, and we'll eventually prove that that the space of such curves is sequentially compact. Of course, these curves will always be causal curves, and we'll always apply it only for curves that go from P to Q, because we have fixed some points and we want only to show that that family of curves is compact.